Hi everyone. Today we will briefly explain how eigenvalues and eigenvectors work in PCA, a key tool for dimensionality reduction. The presentation includes three parts. What are eigenvalues and eigenvectors? Their specific roles in PCA, and their application in engineering. Part 1. What are eigenvalues and eigenvectors? From the class, we know that in linear algebra, for an n-order square matrix A, if there's a non-zero vector v and a constant lambda satisfying A v equals lambda v, then lambda is the eigenvalue, representing the scaling factor when the matrix transforms the vector. V is the eigenvector, the direction that remains unchanged during the transformation, and it only scales. In PCA, we focus on these two forms the data covariance matrix. They reflect data's variance description and co-directions. Part 2. Their specific roles in PCA. First, eigenvectors define the principal component's directions. They act as new low-dimensional axes. Each eigenvector corresponds to one principal component, and they are orthogonal, so no information redundancy. The first eigenvector with the largest eigenvalue is the direction of maximum data variance, retaining the most information. Second, eigenvalues measure information content. Larger eigenvalues mean more information the corresponding eigenvector carries. We select top k eigenvectors by two standards: eigenvalues more than 1, or cumulative contribution rate more than 85%, to reduce dimensions without much information loss. Finally, the synergy completes dimensionality reduction. Standardized data, computer covariance matrix, decompose for eigenvalues and eigenvectors. Select top k and project data to get low-dimensional results. For example, 10-dimension environmental data can be compressed to 2D with 90% information retained via top 2 eigenvectors. And its calculation steps are as follows. 1. Data standardization. Perform standardization on the original data to eliminate differences in dimensions. The Z-score standardization is commonly used like this, where xi is the original value, mu I is the mean, and sigma I is the standard deviation. 2. Calculate the covariance matrix. The standardized data matrix Bx. The formula for calculating the covariance matrix C is this, where n is the number of samples and xt is the transpose of the matrix. 3. Eigenvalue decomposition. Solve the characteristic equation of the covariance matrix C to obtain eigenvalues lambda and eigenvectors v. Eigenvalues represent the variance of the data in the corresponding direction, and eigenvectors represent the direction of the principal components. 4. Select principal components. Sort the eigenvalues in descending order and select the eigenvectors corresponding to the top k largest eigenvalues to return most of the variance. For example, if the first two principal components can explain more than 95% of the variance, they can be retained. 5. Data projection. Multiply the standardized data matrix X by the select eigenvectors matrix Vk to get the dimensionality. Reduce data matrix X, where Vk consists of the top k eigenvectors. Next, My partner will share the third part, the application in engineering.
Hello everyone, today I will use a real case from the China undergraduate mathematical context in modeling problem A to help you understand the core application of eigenvalues and eigenvectors in engineering vibration control of high-pressure fuel pipes. High-pressure fuel pipes are the lifeline of the fuel systems in automobiles and construction machinery, responsible for delivering high-pressure fuel. However, they are most vulnerable to one risk: resonance. When the frequency of fuel pressure impact is close to a pipe's own natural frequency, the amplitude can instantly increase by more than 20 times, from millimeters to centimeters, directly causing the pipe to rupture, fuel leakage, and even fires with serious consequences. Eigenvalues and eigenvectors in linear algebra can accurately calculate the natural frequency and vibration mode of the fuel pipe, helping us mitigate risks proactively. And next, I will explain the entire process from modeling to application step by step. First, reasonable simplification is necessary for engineering modeling. We simplify the complex high-pressure fuel pipe into a fixed beam model commonly used in mechanics. This simplification does not affect the core logic, but also makes calculations more efficient, which is the most common approach in engineering. Based on this model, the vibration of the fuel pipe follows the dynamic equation, like this. Here, K is the stiffness matrix related to the elastic modulus and moment of inertia of the pipe's cross-section, reflecting the pipe's resonance. M is the mass matrix determined by the pipe's density and length, reflecting the magnitude. Ft is the periodic pressure impact force. Since the pressure impact is periodic, this equation can be directly transformed into a generalized eigenvalue problem. K times V equal to lambda times M times V. This is very similar to A times V equal to lambda times V that we learned in linear algebra, except for the addition of the mass matrix M. This is because inertia must be considered in vibration, which is a reasonable extension of undergraduate knowledge and a highlight of the modeling for this problem. By substituting these values into matrices K and M, we can calculate the eigenvalues lambda and eigenvectors V. The core value of this step lies in the clear physical significance of eigenvalues and eigenvectors. The eigenvalue lambda can be directly converted into the pipe's natural frequency omega through this formula. After a precise calculation with the data, we obtain the first-order natural frequency omega-1 equal to 55. This is the most critical frequency because it corresponds to the largest amplitude, and this is most likely to cause resonance. The eigenvector V corresponds to the vibration mode shape. V1 equal to 0, 0.3, 0.6 means that the amplitude at the middle of the pipe is the largest, while the two ends are almost stationary. This clearly tells us that the weak point of the pipe is in the middle, which will rupture first during resonance. We have designed two feasible solutions. Let's first look at solution 1. Shortening the fuel pipe length from 1.2 meters to 1 meters. This is the solution with the lowest cost and easiest implementation. After shortening the length, the stiffness matrix K will increase accordingly. The corresponding eigenvalue lambda will raise from 1.2 times 10 power 7 to 1.8 times 10.7. And the natural frequency omega-1 will also increase from 55 to 68. Now, let's look at the frequency difference again. It completely jumped out of the resonance high-rate zone, directly solving the problem. Solution 2 is to replace the material, changing conventional carbon steel to titanium alloy. With the elastic modulus E decreasing from 210 GPa to 110 GPa. Although this can also reduce the natural frequency to 39 to avoid resonance, but the cost is more than 10 times that of solution 1, which is not cost-effective in engineering. Today, through the case of high-pressure fuel pipes, we can clearly say that eigenvalues and eigenvectors are not abstract mathematical concepts but quantitative tools for solving engineering problems. First, the eigenvalue lambda is the ruler of the inherent properties of the system, directly corresponding to the natural frequency here, helping us find the root cause of resonance risks. Second, the eigenvector V is the map of the system's response shape, helping us locate the weak points of the fuel pipe. Third, the combination of the two realizes a closed loop from mathematical modeling to engineering decision-making. This is precisely the core value of linear algebra in the fields of science and engineering. That's all for my explanation of the application of eigenvalues and eigenvectors. Thank you all.